Okay, lab analysis. Now, we did all our data collection and we got this nice graph here. Now we have to figure out what is going on here. We do the evaluation of data, right? So, evaluation of data is largely analyzing these functions here. So the evaluation of data, all right? We had two different functions. We looked at velocity versus time and position versus time. We're actually going to start with velocity versus time here. So v versus t. This relationship was linear, meaning it was a straight, direct relationship. So velocity is proportional to time. So the velocity of the cart was proportional to the length of time it was running. The experimental equation, okay, that is the equation of the line. And it's a little bit hard to see in the video probably, but on your graphs it said Vx equals mt plus b, and then it says m slope, it's got a number with units, b y-intercept, it's got a number with units, correlation, RMSE, and so on. The RMSE number is not important to us. Correlation is sort of important. That, if it's 1.0 or 0.999, it's a very good correlation. We use the linear fit line on the velocity versus time graph. So it gives us the equation. We're going to write it a little bit differently. We're not going to write the capital Vx that the software gives it. We're just going to call it V equals, and we're going to put in the number here, 0.67 meters per second. Now this is called, again, the experimental equation. And we're going to continue on. So that's the y variable, that's m. The x variable is t, plus the y-intercept, which is 0.11 meters per second. So that's our experimental.
Is there a great bag that was up there? There was.
Yeah, I'm just recording a video. No, you're good. I should have closed the door. All right, experimental equation. Yeah, I found it under the desk. That's it, right there. So now, we got to figure out what the slope and y-intercept mean here. All right? Well, the y-intercept, right? Any y-intercept is the value of the y variable at time equal to 0. So the value of the y variable at time equals 0 is this. So it's the value of the velocity at time 0. Velocity at time 0. That's what we call initial velocity. The velocity at time equal to 0. You could put a 0 in for t into this function, this equation, and it would be v equals 0 plus 0.11. So the velocity at t equal to 0 would be equal to 0.11. We call it the initial velocity. It has a symbol v with a little I next to it. Okay? From there, we look at the slope. All right, the slope here, 0.67 meters per second. So that's the rise over run. That's how much the velocity is changing each second. Right? Each second the velocity is changing. It's changing by positive, because it's a positive slope, 0.67 meters per second each second. We call this acceleration, A-C-C-I-O-N, acceleration. And its symbol is a lowercase a. So that's our experimental equation for velocity versus time. And we've explained everything here, so this is new. The slope of velocity versus time is acceleration, how much velocity is changing each second. The y-intercept is the initial velocity. All right, very good. This goes in your lab report here. Oh, rats, my phone's ringing. Let's see if it rings again. Nope, just once. I don't get that. All right, so let's look at x versus t now. So x versus t, we saw that position was not proportional to time. All right? It ends up that we do a quadratic fit. So it was the relationship between x and t, or position in time, I should say, probably, is quadratic. That's the fit line we used. Now, look here. It's hard to see in the video, I know. It said x equals at squared. I'm going to write it out here. I didn't write it here, but I'm going to write the general form here. X equals at squared plus bt plus c, right? That's the first thing it says here. A little bit different of a window here. Then it tells you what a is, tells you what b is, tells you what c is. Then there's these little plus minus things in the graph. Those don't matter. You don't need to include those. Correlation and root mean square. So a very good correlation. We see this nice, this is called the top opening parabola. It's a curved relationship. I'm going to put the numbers in. X equals 0.34 or 336. I'm just going to do 34 times t squared. Now, I'm leaving a little space there because the units are going to go in there. Plus b, which is 0.11 times t, plus c. Now, or not c, plus negative 0.002. So I'm just going to call that 0.0. And it's actually negative, but negative 0 isn't really a thing, right? So we'll just call it 0, our c variable. Mine was negligible. So small it doesn't matter. Negligible. Good vocab word for physics. Now, the units here and the terms a, b, and c. What do they mean? Well, that's the million-dollar question. Let's start at the end here, right? This term here, let me just make this look kind of uniform. This term here is our what? It's our position when time equals 0, which is our initial position. Very similar to the graph up here. Its variable is an x with an I, a lowercase x with a little I, initial position. This is also an experimental equation here. Now, since it's position, right, it should have units of meters. Cool. 0.11 now. What the heck's that? Well, 0.11. Where did I see that number before? Oh, I saw it up here. Right? Meters, 0.11 meters per second. That was the initial velocity. Well, it is down here also. So that term is our initial velocity. Right? So it's meters per second. And it should be meters per second because each one of these terms has to end up having units of meters, right? If we were going to put it in time here. We put in time in seconds, and the seconds would cancel with the seconds down here. All right, so that would leave me with meters on this unit. Meters on this unit, this one will have to be meters as well. This one's going to end up being meters per second squared. Okay, so the initial velocity variable is VI. Very good. And what's this term? Meters per second squared. That's an interesting unit, meters per second squared. I got meters in 2 seconds up here. Are those equivalent? meters per second, and meters per second squared. Well, I'll do a little side calculation down here. So a meter per second. Do a keep change flip. This is like meters per second divided by seconds over 1, right? So when you divide a fraction, you bring this one up top, but you have to flip it, right? So it's meters per second times 1 over seconds, right? Which then goes to meters over seconds times second squared. So that unit of meters per second is equivalent to meters per second squared. I don't love using this meters per second squared as a unit. So these both have the same units, these two terms in these equations, capital A term and the slope of this line. Well, look, this is about half of that. In fact, that's what it should be. It's 1/2 of the acceleration. All right? So now, that's our evaluation of data. We state the relationship. Velocity was directly proportional to time. The relationship between position and time is quadratic. We write the experimental equations, V equals, and you're putting in the units on all the terms, and that goes in our evaluation of data section. We define what the slope and y-intercepts are here. This one wasn't as easy, right? We kind of had to make some guesses, and I had to tell you what the answer was in the end there. The final thing in your conclusion is to write the general equations, right? So your general equations. All right, so your general equations now. All we do is take the equations, our experimental equations, and replace the numbers, right? Replace your numbers, these are your experimental numbers, with symbols to represent any number here, right? So this is always going to be acceleration, that's always going to be in initial velocity. But you could have any initial velocity and any acceleration. It just depends on what the physical system is doing. So the general equations, we just take our experimental equations. So it's V equals, and we put in the variable, AT plus V initial, and X equals 1/2 AT squared plus V initial T plus initial position X initial. Those are our general equations. Now, there's one last thing I want to show you here. This equation, the slope of the line, you could solve for the slope of the line here, A. So I'll do the side calculation down here. These are the two main general equations. But the fact that the slope of the velocity versus time is acceleration is probably the most important thing. In fact, if you think of go back to just a rough sketch of the velocity versus time graph, right? Went up like this. Well, the slope of this line is rise over run, right? Well, the rise is change in velocity. The run is change in time, right? So if the slope of the line is change in velocity over change in time. And that is the definition of acceleration. Or we can solve for it here. We can say, okay, V equals AT plus V initial. I'm going to solve this for A, so I'm going to subtract off V initial from both sides. All right, so I have V minus V initial equals AT. All right, divide both sides by T to get rid of the T over here. All right, I have V minus V initial over T equals A. Well, V minus V initial, that's V final minus V initial, really. That's usually what we put in here. We usually put an F here to call that V final. So we'll call that V final. We'll call that V final, V final. V final minus V initial is just delta V. And with a T, it's always a delta T. Even if there's no delta in front of the T, it's a delta T. It's in length of time. So there you go. So now these general equations, they go in your conclusion. follow the instructions in the rubric and on the lab instructions, and do your best to write this lab up. I'll post a scan of this along with this video.